In this lesson, we're going to examine how we can actually solve exponential equations, at times using exponents, but other times using logarithms. Logarithms are actually kind of a shortcut that allows us to solve an exponential equation that isn't a nice one. Basics. To solve an exponential equation, we want to have the same base on each side. If our bases are the same, then the exponents have to be the same, kind of like we did with logarithms yesterday. So look at this first equation here. And I'm hoping in our heads we can actually solve this and know that 2 to the power 3 makes 8. But to think about exponential form, how to solve it, really what I want to do is say, okay, I want to make my bases the same. If they're both the same number, then my exponents have to be the same. X has to be 3. That allows me to solve something that's slightly more complicated. Like a b, I might not be able to think in my head what the answer is, but I know that if I can make both of these the same number, same base, I always want to make it the exponential part, 3, okay, then I could solve the exponent. So I think to myself, 3 to the power of what makes 27? Well, 3 to the 3. Okay, my bases are the same, so my exponents have to be the same. So all I need to do is solve the exponential part. 3 minus 2, okay, x has to be 1. Okay, you guys try one here. Let's try C. Okay, I want to make my bases the same. I can't make 4 into 32. Like 4 to the 2 is 16, and 4 to the 3 is 64. So in this case, I can't make them the same directly. What I need to do instead is make both of my bases different to be able to make them into the same value. So what base can I make into a 4 and also a 32? Well, make 2 squared be 4, and 2 to the 5 be 32. Those are different versions of that same number. Now my exponents are on the outside here, haven't changed. Now my bases are the same, yes, but I have to deal with these little exponents inside the brackets first. I need to think myself, what do I do with powers to powers? What I do with those usually is multiply. So this is the left side, and this is the right side. Now my bases are the same. I'm going to solve the equations. And there's my exponential parts on the top. I'm going to solve this. Numbers on one side, letters on the other. 3x is 9, so x is 3. I've solved that exponential equation. In that case, I had to make both my bases the same because I couldn't make a 4 into a 32. I'll try a couple more. Any messy things here? What can I do with these? Oh, bases the same. Well, 2 is a 2. I can't really do anything to it. I can't make it any different than that. I need to think over here. I want to make these into bases of 2's. So I have to think to myself, well, what is that? That's 2 squared is 4. 2 cubed is 8. And a root sign means I got like a half on here, right? So what can I do with that? Well, exponent rules. Power to a power. That's going to give me 3 times 1/2, which is like 1.5. I'm going to use decimals, that's fine. And bases are the same and are multiplying. I have an exponent rule for that. I can add my exponents. Ooh, now my bases are the same. I can solve the exponents. That will be 2.5. Okay, so I don't need calculators to do these. I can get exact answers by using similar bases. Okay, I'll try one tricky one here at the end. I have no exponent rules that deal with things that are being added. That's not one of our exponent rules. Bases multiplying, bases dividing, powers of powers are fine, but I have nothing with a plus sign. So I have to think of this in a different way. What I need you guys to think about is that this actually means that, right? Bases are the same, and exponents add. The rest is still the same. What do I notice about both these expressions, or the left-hand expressions? I notice I have a 3 to the x plus another 3 to the x, which means I can common factor. If I take 3 to the x out, I'll be left with my 3 squared plus that divided by that makes 1. Now, why would I want to do that? Well, let's see what happens when I do the stuff in the brackets. 3 squared plus 1 makes 10. I can divide both sides by 10, and I'll get 3 to the x equals, hey, that's like that, right? x is 1. Okay, so that's kind of a tricky question. A way of dealing with things when you have a plus sign is try common factoring. But to common factor, you may have to make sure you have the same thing in both. Hey, problems. Sometimes we can't make the bases the same. For example, 5 to the x is 53. I can't make 53 out of a 5. That's not possible. So if that's the case, what we're going to do is we're going to use our logarithms. We're going to take the log of both sides and then use our power rule to solve this. Because we're just using a log of both sides, we're assuming it's going to be the common base, base 10, and we can then solve for exponent using our calculator. So for example, let's try the first one here. 5 to the x is 53. I can't make 5 to the something come out to 53. That's not possible. What I need to do instead is say, okay, well, let's take the log of one side. What I would do to one side, I do to the other. And these are base 10s because I didn't put a base in there. My power rule, x can come down in front. And if I want to get x by itself, I have to divide out the log 5, right? But if I divide one side, I have to divide the other side. So just to rewrite it, to show you what we have here, we have x equals log 53, which is base 10, over log 5, which is also base 10, which means that I can put this in my calculator. If you do, you should get 2.47. So this is how I can solve an exponential equation, which is what the question really is, exponential equations, without necessarily using exponents, but instead using a logarithm. Hey, you guys can try B. Same idea. I can't make a 2 into a 364, so we'll use our logarithms. Take our base, our power down, power rule. We're going to solve this using our calculators. If you put in your calculator, hopefully you guys got 8.1. Okay, so those are some basic ones. Try things more complicated. The same ideas exist still. I can't make a 5 into a 130, but I can take the log of both sides. And if I take my power down to the front, right, I'm going to write down as 2x plus 3 in brackets, because that whole thing was my exponent. And so if I divide out the logs, I'll have log 130 over log 5. And I can use my calculator on the right-hand side. I'm going to make an ugly decimal, but that's okay. 3.0243. I still have 2x plus 3 over here. So we need to solve this using our basic algebra stuff. And I got 2x equals 0.0243. There's more decimals than that, but get the hang of it. And divide it out, and I get 0.122. Okay, so we can have exponents that are made of parts and pieces. It still works the same way. Let's try the next one. What can I do with this? What? I want to make it easier, right? I only want to have one base on each side. So let's divide out that 50. If I divide the right side by 50, I've got to divide the left side by 50. So I end up with 7. Makes it easier. It makes it one base per side, which means I can apply log laws or exponent rules now. I can't make a 2 into a 7. So I'm going to take a logarithm. Right, bring my power down. Okay, this part actually takes longer to write out than to do the math, because we know what's going to happen here. So log 7 over log 2. Into our calculator we go. I'm going to make an ugly decimal. That's okay. We'll get x over 5 is 2.807 dot dot dot. That's what x over 5 is. I want x. So multiply by 5. And you should get approximately 14.04. Let's try the last one here, letter E. What can we do with E? E is messy looking. Let's think about this. What can I do? What can I do? Well, we've dealt with root signs before. We had a root 8 earlier. We turned into a 2. What's root 1296? That's something that's actually easier to work with. Let's see if we can figure out what that is. It turns out that that's a perfect square. So even though things look more complicated, see if you can simplify them first. Hey, my bases are the same right now. I don't need to apply logs or exponentials. My bases are the same, my exponents are the same. 2x minus x goes negative 4. Hey, x is negative 4. So sometimes we're going to come across things where we don't have to apply the log laws. Don't just blindly trust we're doing the same thing every single time. I need you to think a little bit. Okay, we're going to try a couple of applications here. We got some money. We're going to invest it. It's going to make 7% yearly, compounded semi-annually. How long will it take to double? Okay, that's a kind of a standard question. So our formula for money, our future value, depends on our present value, our rate over 100 compounding periods, and total number of periods. Okay, this is the formula we learned for compound interest. So how much money do we start with? What's our present value? Well, right now we don't know how much, but we want to double. So really, it could be any number you want as your present value, as long as your future value is doubled. And 1 and 2 would be the easiest numbers to work with. Our rate is 7%. We're going to compound that semi-annually, which you might remember is 2. And we're going to do it twice a year for n number of years. That's what we want to find out. Okay, well, what can I do with this? Well, let's make it simpler first of all. Oops, that's an equal sign there, not a plus sign. 1 plus 7 divided by 0.035, just 2n. It kind of looks like an exponential equation here, right? 1.035 to the 2n. I don't really need this one because it doesn't do anything. So really, I have this exponential equation. Well, I can solve that using logarithms. I take the log of one side. I take the log of the other side. My exponent comes down in front. I divide out my logarithm into our calculator we go, and you should get, how did I get here, 20.1488, and that's 2n. So n divided by 2 is approximately 10.07 years. Okay? That's one of the things we couldn't really solve for compound interest before, is the length of time. Well, we can now, using a logarithm. Okay? It's a nice, good application of that. And one of the other applications we always talked about was half-lives. You might remember that a half-life is always your initial value times half to the power of x over your half-life, and it depends on what. That was kind of our standard equation for this. Well, let's take a look at this question here. We got polonium. Half-life is 200 years. Write an equation for the amount remaining of a 20-gram sample after X years. So how much remains? Well, we start at 20 grams. It's cutting in half. And it's going to do this every 200 years. There's our equation. And how much remains after 100 years, 450 years? Well, we can figure that out. After 100 years, which is, if you want to say it, a half-life. Anyway, this is a half. You should get approximately 14.14 grams. So it didn't quite cut in half, right? Half of a half. And we can do the same thing for 450, which is more than a half-life. It's more than 2 half-lives, in fact. 2 and a quarter. You should get 4.2 grams. So that makes sense. So it's cut in half more than twice. And part C. Okay, so I want to solve for the exponent. I want it to come up to 2. It started at 20. And I got x over 200. Okay, I want to solve this. To solve this, it's an exponential equation. We want one number per side. I'm going to divide out 20 here, divide out the 20 there. I can use 0.5 or 1/2. Doesn't make a difference which, okay? Okay, there's an exponential equation. To solve it, we can use logarithms. log of 0.1 equals log of 0.5 x over 200. Bring our exponent down in front. Log 0.5, log 0.1. I want to get my x by itself. Using our calculators, we can figure out what that left-hand side is there. I got 3.3219 dot 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 times it by 200, and you should get approximately 664.39 years. So again, the standard way of solving a half-life question. We can use logarithms now to find unknown times. All right, last thing. I want you to solve these two decimal places. So we've been talking about logarithms, we've been using logarithms. You might have to use logarithms in here. I need you to think. It's often we start doing the word problems and we forget some of the basics. Let's try the first one. Log 2, 210. Well, log 2, 210 is not something from my calculator. And 2 to the power of something doesn't make 210. I can make 256. I can make, that's 2 to the 8. I can make 2 to the 128. It's 2 to the 7. So somewhere between 7 and 8 is the answer, but I can't solve it the way it is. So let's think of this as the question that 2 to the something makes 210. Oh, well, that's a logarithm exponential equation. If I take the log of both sides, I can now deal in common base instead of base 2. My exponent comes down. My x will be log of 210 over log 2, which is something I can put in my calculator, and I can calculate. And it turns out I was right. Between 7 and 8, it's 7.71. Try B. Hopefully you guys can figure this one out now. Okay, 4 to the what makes 20? Well, I can't make 4 to the 2. 4 squared is 16. 4 cubed is 64. So it's somewhere between 2 and 3, but I can't figure it out. If I turn this into an exponential equation, however, we can do what we did a second ago, right? I'm going to cheat here. We know what's going to happen. It's going to be log 20 over log 4 into our calculator common base. Hopefully you guys got 2.16, which should make sense between 2 and 3. And try the last one here. Log 2 5/8. I don't like the format of this. Let's change it. That's 8 to the 1/5. You know what? I can actually calculate this. So all I need to do is get rid of the 1/5. Let's rewrite that. Well, our basic log rule. Right, power rule. Well, I got 1/5. 2 to the 3 is 8. So I get that. I got 3/5. Yeah, so I didn't need to use a logarithm to solve that one. I just need to go back to a different format. That's our challenge here, right? We're working in different formats all the time, forwards and backwards and all kinds of stuff. Okay, that's the end of that lesson. Try some of the homework questions, there they are. Okay, just do A, C, and E for those questions. If you're stuck, come see me, and we'll move on to solving some logarithmic things tomorrow.